Hello everyone. Today we are going to be looking at coordinate systems. Now in this section, we're going to go more deeper into the basis set and get more information out of it. And not only we will see how we can utilize basis set to our advantage, but at the same time how this basis set will help us to connect any kind of a vector space to the appropriate r-dimensional systems or the spaces. And it is going to be this basis set which is going to be the key for us. Okay, now remember one thing from the last section. We talked about a basis set. And we said a basis set is the one which represents an infinite set in a very small number of vectors. But there was also another thing there. The basis set was not unique. We could have more than one basis set to represent the same vector space. So if you look at that sense, then basis set was not working. But if you look at it from a different angle to the same basis set, that is going to be a key part for us. So the first thing we're going to look at is a unique representation theorem. What this theorem says, that if I am given any basis set, okay, it doesn't matter what, it is one basis set is needed, then for every vector x, which is related to that basis set, we will have a unique set of scalars. Now here's the catch. Given any basis set of a vector space, and if I look at any vector x, because this vector x can be written as a linear combination, so that any vector x, for this one we will have a unique set of scalars such that x can be written as a linear combination of the basis element. Okay, and we're assuming that my basis set has, say, elements b1 to bn. That's what we're assuming. And remember, the number of elements in the basis set is actually the dimension of the vector space. So here, if I say I'm having n elements in the basis set, so my dimension of V is n. So I'm just trying to recollect things we have learned earlier. But what is the main important thing for us at this point is that given any basis set, I will be able to find a unique set of scalars relevant to this basis set such that any vector x in the vector space V can be written as a linear combination of these scalars in accordance with the basis set. Okay, now we're going to prove this one. And how do we prove? We use contradiction to prove it. So let's look at the proof. If suppose any vector x we have in a vector space V, and B is the basis set of that vector space V. And we're assuming that B has n vectors, v1 to v1. And we are saying contradiction, that means I will have two set of scalars. And they're totally different, such that my x can be written as a combination of c1, v1 plus cn, vn. At the same time, there's another set of scalars, such that my x can be written as d1, x1 plus ... dn, xn. And this is we're using the theorem that each of the CIs are not the same as the DIs. A very important concept. Okay, so let's look at that. So now here's my proof. I say as my x can be written as c1 v1 plus ... cn vn, and similarly d1 v1 plus ... dn vn. So these are basically both representing the same x. So we can say c1 v1 plus cn vn equals d1 v1 up to dn. And now simple algebra. Take all the elements from the right hand side to the left hand side, combine the elements which are common to the vector v1, and we get c1 minus d1 times v1 plus ... cn minus dn times vn equals 0. Now that's simple algebra. But now we have to start looking in terms of where is my vi's coming from. Now in this linear combination of vectors, notice that where is my v1? My v1 over here, guys, v1 to vn are elements of the basis set. Now remember basis set definition. Elements are linearly independent. So if my elements of the set are linearly independent, that means each of the scalars or the coefficients or the constant of the weights, whatever you want to call, is equal to 0. That means C1 minus D1 equal to 0, Cn minus Dn equals 0. So that means each of the Ci's are nothing but the Di's. So what we started as a proof is contradictory. And hence, we have come to a realization that any vector x of the vector space given to or relative to a basis set will have a unique scalars C1 to Cn such that x can be written as a linear combination of those scalars with v1 to v1 and that little v1s to vn are the elements of the basis set. Remember, this basis set B is v1 to vn. Okay, now there is what is going to give us a definition which is going to play a key role for our theory later on. Okay, let's look at the definition. So this, guys, is my definition. If I have a basis set for any vector space V, and I can write my x, let x be an element of V. Because B is a basis set, S can be written as a linear combination of these elements of the basis set B1 to Bn. So clearly remember, what does this look like, guys? This is a vector equation. And I can change a vector equation to a matrix equation where B1s to Bn, these are vectors. Remember, these are the elements of the basis set B. So I can write the B1s as a matrix. So this is my matrix A. And C1 to Cn are scalars is the matrix, say, S. So this one, guys, remember, is a matrix equation. Okay, so coming back, we have a basis set for a vector space V. And every x can be written as a linear combination of the basis set where the Ci's are unique. So we can change this vector equation to a matrix equation. And this, guys, the C1 to Cn, this is what we call. So we're going to give a new name to this vector x we have. We're going to call this as the coordinate vector of x relative to a basis B. Okay, so this is this vector x, which was from the matrix equation, which we learned so many years long ago, is now given a new terminology. We're saying this is the coordinate vector of x relative to the basis B. Or in a short form, it's called the B coordinate vector of x. My recommendation to guys is stick to this definition. Do not go to the short form because it becomes confusing. I always still go to this definition whenever I see a linear combination of vectors of x where I know my b1s to bn's are the basis of a vector space. Automatically in my head, oh, the scalars, when I put them in a vector form, they are the coordinate vector of x relative to the basis B. Okay, that's a thing which we have been seeing for so long, but now we're giving a new terminology. It's same old stuff, guys. Okay, now let's look at some observations here. This, the vector x, coordinate vector relative to a basis B, is a vector in Rn. Remember, how many elements my vector B had? N elements. That means it will have n scalars for the vector x. So every coordinate vector relative to a basis set will be an element of R dimensional space, and that space will have the same dimensional depending upon how many vectors are present in the basis set. And notice what we have got. Suppose this was my vector space V, and x is any element. And then I have a basis set, this B, which basically spans the whole vector space. So every vector x can be now mapped from this relative to the spaces B because of the unique scalarness. So there's a mapping from this vector x to an element of Rn. So remember, this one is now going to be mapped on to elements of Rn based on the spaces set. So this will be one element, say C1 to Cn. Okay, so this is called a mapping, which we will go in details later on. So this mapping is called the coordinate mapping, which is determined by the basis set of the vector space V. Okay, I'm just introducing it to you, and I will come back later on and go deeper into this coordinate mapping scenario. So now what we're going to do is we're going to do a lot of examples to get us familiarizing with all these coordinate vectors relative to a basis set. Okay, let's start with examples now. So the first example. Sorry guys, it's cutting off, but if you go online on D12, as I said earlier, my notes are over there written much more clearly. So when you're looking at the video, going over the video, make sure you have the notes in front of you. Okay, now let's start with an example. You say consider an x in R2. Okay, so this is consider, guys. An x in R2. R2 is a vector space, we all know that. Now every element in R2 can be written as a linear combination of the standard basis. In other words, my x, 1, 6, can be written as 1 times 1 and 0, which is my E1 here, and 6 times 0 and 1, which is my E2. So this one, guys, so this vector x in R2 can be written as a combination of 1 times E1. So this can be written as 1 times E1 plus 6 times E2. See this one here. Now we're going to say my C1 is 1 and C2 is 6. So in other words, this vector 1 and 6 is nothing but the coordinate vector of x relative to the standard basis B1, 1 and 6. So in other words, if you know a standard basis of an R-dimensional space, every vector x is nothing but the coordinate vector of x relative to the standard basis. Very important, remember, every vector of x of a vector space is nothing but the coordinate vector of x relative to the standard basis. This B1, guys, is the standard basis. In our problem here, B1 is the standard basis of R2. Now, we also said that we can have more than one basis set for a vector spaces. So now, let's pick up another basis set, B2. I'm going to pick up another basis set of R2, which is given by B1 is 1 and 0, but B2 is 1 and 2. Now, we would like to see how the vector x, 1 and 6, can be written as a linear combination of this, and our job is to figure out the coordinate vector of x, this vector 1 and 6, relative to the basis set B2. The first one was pretty simple. Okay, now we have to actually do some computational. Okay, remember what I'm saying. I want to find the relative vector of x, coordinate vector of x relative to the basis B2. So in other words, I want to find x1 and x2. Now, this is my vector x, 1 and 6. And I want to find the coordinate vector, which is x1 times the basis set B1 plus x2 times B2. Because remember, every vector x can be written as a linear combination of B1 and B2 for the basis set capital B2. Now, this is a vector equation, if you remember. I can write a vector equation. As usual, this is a vector equation. I'm going to write this vector equation as a matrix equation, which is section 1.4 of the Lay's book. Now, so clearly my 1 and 6 can be written as 1, 0, 1, 2, x1, x2. Now, what is this? Do you remember? Nice little problem. It's a matrix equation. Now, in other words, I want to see, will I be able to find x1 and x2 relative to this matrix equation? Going back to, guys, section 1, 2. In other words, solving this matrix equation. Okay, so which basically also amount to solving a linear system. What are we going to do? We're going to put this elements, and this 1 and 6 is the constant element. So notice this one can be written as what? x1 plus x2 equals 1 and 2x2 equals 6. So I can write this linear system as an augment matrix, solve it. When we solve it, what do we get? We get that this matrix, when you remember we apply the algorithm, we get the identity matrix, and this one is my x1 and this one is my x2. So these are the variables, that these are the coordinate vectors relative to the basis b2 for the vector x, where my x is given as 1 and 6. So you basically get the x1s and x2. So this is what we are looking for. So what does this mean? This means, so when I can write this vector x, 1 and 6, as minus 2 times the vector b1, 1 and 0, plus 3 times the vector 1 and 2, which is basically minus 2 times b1 plus 3 times b2. What simply it means is that this vector x relative to the basis set b2 is going minus 2 units in the b1 direction, because remember these are two, our basis set, and 3 is going in the b2 direction. So let's look at the graphs on the next page to give you what a visual representation of what I'm talking about. It's all just basic numbers I'm saying here. Let's look at this one here. Now we are all familiar with the standard basis. So if I have the xy plane and the R2, that means I have my two axes x and y here, which are perpendicular to each other. The standard basis basically means here is like this is my E1. So I'm going 1 unit here, and each of them are perpendicular to each other. So the standard basis is 1, 0, 0, 1. So this one, remember, is E1 is 1, 0. So that means this is a point, this point is 1 here, and this point is 1 and 6. So remember, this is 6. This simply means you're going 1 unit in the direction of x-axis, or E1, and you're going 6 units in the direction of E2, which is the y direction here for us. Okay, so this x, guys, is my E1, and this y is my E2. Okay, on the other hand, if I take the same graph and I just tilt the E2, just a little tilt, oops, hold on guys, give me a second. Okay, so I take this now y, now we are going to have a basis set, so I'm just tilting it a little bit. And now, remember, this is 1 and 2. So this is 1 and 2. Do you see that? So I'm going to basically go in this direction. So these are horizontal lines. That's my B1 is the same as this B1, E1. But my B2 is different than this. Here, it's a little slanting lines. So this is my B2 and this is my B1. So I'm basically going B1 and then B2. Then this is my... Now remember, every time you have to go is this one is B2 is 1 and 2. So basically this is 1 and 2. So basically we're going like this here. So I'm basically taking this one, then this one, and here. So this is what I'm doing. Do you see this one here? Here and then here. So this is my B2, guys. Do you see this here? This is my B2. Okay, so this is my B2 and this B1 is my E1. Okay, so then I just draw parallel lines. And now, when I look at my basis set B2, so relative to this, what is the coordinate vector of x relative to the basis B2 is minus 2 and 3. It means I'm going minus 2 units on the B1 direction and then 3 units up in the B2 direction. So this is the point B2, the coordinate vector of x relative to B2. Now when I'm going to put both of them on the same graph, notice what's going to happen. So remember, this is my B2 here. Okay, I'm just trying, okay, hopefully you get this one. Remember, this is my B2. The black one here is the B2, is the red one here. Okay. Okay, so when I put these two, different, the r-dimensional spaces, they're both representing R2. When I put them together, you will see that this point is going to actually coincide with this point. This is what's going on. So this point, when I look at from the xy, remember my x is E1 and my y is E2. And this point, it depends upon how I'm looking at my axis. One is like 90 degrees, x and y are 90 degrees to each other. And the next axis is a little tilted, okay? But the point x depends upon what basis set you're looking at, is like the same point, but the way you look at it is different, okay? So that's the bigger picture. It means the same x, when I'm looking at from one basis set, looks differently, but the position is the same. If you put all those basis set together, it's what basis set we are looking at. Okay. So now we are going to add some theory to it. So remember, here I had this vector x. You see this one? Now this x, when relative to the basis b2, is written like b1, b2. Remember, this was what? X was what? x1, b1 plus x2, b2. And this b1, b2 is coming from the basis set capital B2. Okay, so when we wrote this vector equation in terms of the matrix equation, now this vector of x1 and x2 is nothing but the coordinate vector. So this is what we call the coordinate vector of x relative to the basis set B2. Remember, this is the terminology I'm applying. When you do the calculations, after the calculations are done, we try to relate it to what we have just learned. So we have learned about a coordinate vector relative to a basis set. Okay, so this vector x1 and x2 here, this vector is nothing but the coordinate vector of x, the original vector x here, relative to the basis set B2. And this, when you look at all the basis set, look at the elements of the basis set, you put them in a matrix form. That is called, we're going to give the new name, this is called P. This is the change of coordinate matrix from the basis set B2. Remember this, what is this? This is the coordinate vector of x relative to the basis B1. What was my B1? It was the standard basis. So this matrix changes a vector x from one basis set to another basis set. And that's what we give the name is, and this is the notation, guys, okay? So PB2 is the change of coordinate matrix from one basis set to the standard matrix in R2. Okay, the standard matrix is the matrix which is formed from the standard basis. That's what it simply means. Okay, this PB2, look at the basis set. It is made from the elements of the basis set B2. And now we're going to do some theory which we have learned earlier. Now it is a basis element. That means it's linearly independent. And this matrix is a square matrix. Hence, by the invertible matrix theorem, PB2 is invertible. Hence, the inverse exists. So then what we do? Remember, we have x equals PB2, coordinate vector of x relative to the basis B2. Then I'm going to multiply this whole equation by P inverse B2 on both this, left-hand side. This is, because it's invertible, this is identity, and we get this relationship. Okay, we can generalize this concept, guys, not only just to an R2, but to any dimensional space. What I'm saying is this. If I have a basis set B of an n-dimensional space, that means the elements of the basis set would be n of them, B1 to Bn. Then when I put this in a matrix, all these basis set in a matrix, it becomes the change of coordinate matrix from the basis set B to the standard basis in Rn, or the standard matrix. So let me just write the standard basis over here just to be consistent. This is the standard basis, just to be consistent with what I have. Thus, X can be written as the change of coordinate matrix relative to the basis B multiplied to the coordinate vector of X relative to the same basis. It's invertible. That means this matrix PB is invertible by IMT, inverse exist, and hence I can multiply on both the sides on the left by PB inverse, and hence we see that PB inverse, when acts on X, takes us to the coordinate vector X relative to the basis set B. Now, this is the relationship which takes any element. Now, what is this, guys? This is any element of any vector space. And then, when we have a basis set of this vector space, any vector space, you put them in a column and make a matrix, and take the inverse of that matrix. So what does happen? This coordinate mapping, you see this one, coordinate mapping of B? This coordinate mapping is the one which takes every element of any vector space to an n-dimensional vector space. So what we see is that this coordinate mapping, this one, guys, this coordinate mapping, it is connecting, or the coordinate vector or the coordinate mapping is the one which connects an unfamiliar vector space to the familiar vector space Rn. And that's what we really need, because we're very comfortable with working in R-dimensional spaces. So if you're able to connect the connection, in other words, if you're able to find that coordinate mapping, a coordinate mapping is basically done via coordinate vectors, which basically is working on the scalars corresponding to a basis set. The basis set is needed, but instead we're not working directly with the basis, but you're looking at the scalars which are multiplied to the basis set. Okay, now it's time to do some examples. So the most important thing as to you to remember is this: if I am given a vector space V and given any X element of V, and I'm giving a basis set B, then this vector X is written as PB. This is the change of coordinate, this is basically all the basis set put in this matrix PB, and you find out the coordinate vector of X relative to the basis B. Or this can be written as, because this matrix is invertible, PB inverse X equals the coordinate vector of X relative to the basis set B. So basically, what I'm saying is, if I am given this, these two equations will always hold. So depending upon what the problem is, you just plug in the numbers and get the answers. So here, the first problem is, we're given a basis for an R2-dimensional space, and we're given the coordinate vector. Okay? We would like to find the X, which corresponds, which can be written as a linear combination. In other words, I want to find this X. So what we need is, take the basis set, put that in a matrix, which we call PB, and we are already given the coordinate vector of X relative to the basis set B, and simply do the multiplication, and we get the original vector X, which is also in R2. Okay, now let's go for the other way side. In other words, I'm given the vector X and I'm given the basis set. I would like to find the coordinate vector relative to the basis set B. So in other words, we're going to look at the problem here. Okay, here's the question. It says, find the coordinate vector relative to the basis set of a given vector X, and the basis set is given to us. We have to be given the basis set, guys, important. Otherwise, we cannot work on these problems. So we're given the basis set, and I want to find the coordinate vector. So remember the formula. So what you do is you take the matrix, the basis set, put each of the elements in a matrix form. Now, because you want to find the coordinate vector, we will take the invertible. You can find the inverse of a 2 by 2 matrix. We get this matrix. And then we multiply this matrix with the vector X, which is given to us. It will give us the coordinate vector X relative to the basis set B. And here's our answer. Okay, so we have learned, given a coordinate vector and a basis set, we can find the vector x corresponding to it. We have also worked on an example where we are given the vector x with the basis set and find the coordinate vector of x relative to the basis set. Remember, it's one equation. We just twist it around and move with it. Okay, let's look at one more example. Okay, so here's it. We have given a basis set of a subspace H. And these elements are B1 and B2. They are elements of R3. You can already see that. Minus 3, 2, minus 4. B2 is 7, minus 3, and 5. And we're given a vector x in H, which is 5, 0, minus 2. So clearly, H is it's a subset of R3. We can see that. And this basis set is a subspace. So clearly every subspace, now if I took the spanning set of B, it will make the H. Now H, let me show that over here. If you remember from section 4.1, H is a subspace, if I write it as a spanning set of B1 and B2. Because remember, this is a basis set, every element of this will give us the element of the whole subspace. And every subspace is a vector space. We are asked to find the coordinate vector of x relative to this basis set B. Okay. So in other words, if I'm asked to find a coordinate vector of x relative to this basis set B, what am I saying? Hey, can you give me those scalars? That's what my question is. Can you give me the scalars C1 and C2 such that x can be written as a linear combination of the basis set with respect to C1 and C2. That means x can be written as C1b1 plus C2b2. This, guys, remember, is a vector equation. We're looking for the C1s and C2s. What are we going to do? We are going to write it as a matrix equation. This, guys, is a matrix equation. Which, after this, which I've written it down, basically we are going to get a linear system of equations and we are looking to find the C1s and C2s. That means once again we go back to section 1.2, solve this augment matrix, and we get the two values of C1 and C2 to be 3 and 2. Okay, let's look at a very, very, very important scenario here. This x is an element of H, which is a subspace of R3. Remember, where is this element? This is in R3. And H, we know, is a subspace of R3. R3 is a vector space, we know that. And H also is a vector space. This element can be written as a linear combination of two vectors, 3 and 2. So what's the most important thing we notice? That though the elements of H are in R3, but it is completely determined by the coordinate vectors in R2, because these go handy. You know, we put them in a vector form. Okay? That's the catch. It's not that if you have an element in R2, it will always be having coordinate vectors in R2. Here we have an example of vectors in R3. Their coordinate vectors are in R2. It is possible, guys. Okay, now your job to practice all these problems in book of 5th edition 1 to 12. Practice them. It is going to give you the idea of finding a coordinate vector x relative to the basis set B of any vector space. Thank you.